Je vois que le nombre de participants grimpe encore un peu. On va attendre peut-être encore une petite minute, le temps que tout le monde finisse de se connecter. Puis on débutera. Bon, je pense qu'on va pouvoir débuter. Donc, bonjour à tous de nous avoir rejoints dans ce nouveau séminaire. Donc, aujourd'hui, il ne va pas y avoir de minute verte. Donc, l'équipe MIVEGEC 1.5 s'en excuse. Et on les retrouvera donc, pour le prochain séminaire qui aura lieu dans 2 semaines. Donc, on va pouvoir passer de suite à la présentation du jour qui s'intitule « Impact of insecticide resistance and the efficacy of malaria vector control ». Donc, il va vous être présenté par Priscille BARREAUX, donc, qui est chercheuse en biologie des vecteurs et spécialisée dans l'interaction hôte-parasite. Elle est actuellement en contrat postdoctoral à la Liverpool School of Tropical Medicine en Angleterre. Donc, elle a débuté par une thèse sur les effets sublétaux des insecticides sur le comportement des moustiques responsables du paludisme. Puis, elle a cherché à comprendre l'impact épidémiologique de la résistance aux insecticides sur le comportement et la physiologie des moustiques. Et maintenant, elle s'attaque aux problèmes de santé publique dans les pays du Sud, notamment par le développement d'outils phénotypiques et moléculaires appliqués aux nouvelles méthodes de lutte antivectorielle et par la mise en œuvre de ces méthodes sur le terrain. Priscille, c'est à vous.
Hi, everyone. I would like to start by thanking the MIVEGEC team for inviting me to present my recent work during the seminar and for this introduction. So my talk is about the impact of insecticide resistance on the efficacy of malaria vector control. You probably all know what female mosquitoes do. They annoy people by biting them. And at the same time, they potentially transmit diseases from one person to another. So today I will focus on Anopheles gambiae, the vector of malaria. It mostly bites humans inside houses while they are sleeping at night, but it sometimes also bites animals in animal shelters or outdoors. So now, to avoid disease transmission, the goal is to reduce host-parasite contact and prevent the completion of the parasite development, which lasts around 12 days. Indeed, the more interaction between a host and the vector, the more risk of disease transmission. So one way to limit this interaction between human and the vector is to use insecticide-treated bed nets. ITNs are widely used to fight mosquito bites, and well over 1 billion ITNs were distributed in the last 20 years, resulting in a large decline of malaria cases. So how do ITN work? So until recently, the only insecticide authorized on bed nets were pyrethroids. And when female mosquitoes are exposed to them, they can be repelled before entering houses at night, be irritated upon contact and escape, be killed before, during, or directly after bloodmeal. But some mosquitoes are resistant, they do not die immediately, and fed females are able to finish their gonotrophic cycle. Resistance to pyrethroid is now widespread in the world and threatens the efficacy of vector control tools. And insecticide authorized for vector control, such as pyrethroids, now fail to kill mosquito 24 hours after an exposure. So the WHO method used to monitor resistance in regions with mosquito-borne diseases inform transmission model and are based on single insecticide exposure against young and unfed female after they have emerged from water and mated with male. But the transmission model struggles to predict the impact of resistance on this transmission based on this data. First, because we actually care about the impact of insecticide on mosquito of all ages willing to take a blood meal, and also how it impacts their capacity to survive until they lay eggs. And also we really care about the older mosquitoes able to survive insecticide exposure and able to take at least 2 blood meal in their life, once to acquire the disease and once to transmit the parasite to a host. So here, the green arrow highlights the fact that mosquito probably engage in several gonotrophic cycles during their life. Therefore, to assess the impact of insecticide exposure on disease transmission, it is extremely important to incorporate information on longevity and lifelong blood feeding success. That is why I'm interested in the impact of insecticide on mosquito feeding behavior and survival post-exposure. First, I want to know whether insecticides are repellent, irritant, and toxic enough to influence the normal host searching and blood feeding behavior in resistant mosquitoes. And then test whether or not the presence of insecticide affects the amount of blood ingested by the female. And as only mosquitoes old enough to potentially transmit malaria are of importance, my last question is, do ITN cause delayed mortality? So to answer those questions, I worked with extremely resistant mosquito population from around BARREAUX in Côte d'Ivoire and a resistant strain colonized from Burkina Faso. I tested the permanent 2 treated with deltametrine, but also the olisette net treated with permethrin, and the permanent 3 roof, which is coated with deltametrine and piperonyl butoxide, which is, or PBO, synergies that blocks the activity of enzymes able to break down insecticides. So first, I'm presenting one experiment done in Côte d'Ivoire during my PhD with Matt Thomas at Penn State and Jacob Coel at the University of Neuchâtel. I tested the behavior of 370 mosquitoes collected as larvae in the field in individual cup tests. A 5-minute cup test consists of a plastic cup with an ITN or an untreated net on top, and mosquitoes inside are exposed only if they are interested in the arm lying on the net, as shown in the picture. So I looked at the time spent on the net, the time spent feeding, the feeding success, and daily survival. And mosquitoes were exposed against a permanent 2, a permanent 3, or an untreated net. And I found that mosquitoes exposed to insecticide with PBO, so in blue, spend on average around 1 minute in contact with the net, which is half the average time spent on an ITN without PBO in red, and around 3 times less than the average time spent on an untreated net. Also, the fed female exposed to an untreated net, so in black, spend around 85% of the maximum time in contact with the net, which is significantly more than any other group. And the presence of insecticide reduced the time spent on the net for fed mosquitoes compared to the control. So in the figure 2, fed mosquitoes exposed to an ITN with PBO spend less time feeding on the net than mosquitoes exposed to an ITN without a PBO. And those mosquitoes exposed to an ITN spend less time feeding than mosquitoes exposed to an untreated net. In the figure 3, mosquitoes exposed to an untreated net had a blood feeding success of 60%, those exposed to an ITN 39%, and only 9% of mosquitoes exposed to an ITN with PBO took a blood meal. Mosquito exposed to an ITN with PBO had a shorter lifespan compared to all treatment, and the mosquito exposed to an untreated net survived almost 2 times longer than those exposed to insecticide. But if the mosquito had blood fed, they survived better, except for those exposed to an ITN with PBO, of course. And fed female had an average longevity of 20 days and unfed female of 12 days. ITNs also kills a large proportion of mosquito before 12 days post-exposure. So overall, these results suggest that ITNs retain at least some functionality against highly resistant mosquito. So the presence of insecticide affects the feeding success in short-distance assays, but I wanted to understand whether insecticide affects foraging decision in a semi-field experiment as well. So during 3 months, 4,150 mosquitoes were tested in an enclosure after a pre-exposure to insecticide, and mosquito had the choice between 2 huts, one with a control net and one with an ITN. So the goal was to test if mosquito pre-exposed to insecticide were still able and motivated to host sick, take a blood meal, and whether they will make a choice between the 2 huts that is different from the control group. So in the enclosure, recapture rates were extremely high, with an average of 98% of mosquito alive or dead collected back each morning after release. And 33% of the released mosquito entered one of the 2 huts. Those pre-exposed in cone against an ITN were marginally, so by 3%, more motivated to enter one of the 2 huts compared to mosquito pre-exposed to an untreated net. Considering only mosquito recapture inside huts, there were 4% more mosquito found in huts in which the hosts were protected with an ITN compared to the average. So there was no repellency effect of the ITN in the enclosure as shown in the figure 2. In the figure 3, we see that when tested with damaged net, 36% of the mosquito recapture were found in the veranda. And in the hut with an ITN, around 10% more mosquito were recaptured in the veranda compared to the hut with an untreated net. So here again, you can see the immediate efficacy of ITN is compromised by resistance. There is no effect of pre-exposure to insecticide on the blood feeding success of mosquitoes when considering the total pool of mosquito, as well as in proportion of mosquito entering huts. Mosquitoes that took a blood meal survived better than those that did not take a blood meal, and that effect was more important for mosquito pre-exposed against an untreated net rather than an ITN. So can we conclude about ITN efficacy already? Not yet. We only talked about the immediate effect of insecticide on blood feeding success. So going back to the CAP assays, I was interested in the effect of one insecticide exposure on feeding success over the lifespan. I exposed 460 mosquitoes to an untreated net or a permanent tube, and I looked at the feeding success and and longevity. So I had 2 groups of mosquitoes. In the first group, mosquito had the chance to take a blood meal while being exposed to insecticide. And in the second group, where mosquito were pre-exposed to insecticide before having the opportunity to take a blood meal. So after this first chance to take a blood meal, the mosquito had the opportunity to feed every hour in the absence of insecticide directly on my arm above the rearing cup. So in total, each group had 6 opportunities to take a blood meal. And the feeding success on the succeeding hours of experimentation was always better for the control group, and the presence of insecticide did not completely prevent mosquito from biting in the following hours post-exposure. So after 6 hours of experimentation, around 50% of mosquitoes that were in contact with insecticide did not take any blood meals, against only 16% in the control group. 48% of mosquitoes took a blood meal in on the first opportunity, despite the presence of insecticide, against 21% of mosquitoes that were pre-exposed to insecticide before being able to take a blood meal. And at the end of the day, only 34% didn't take any blood meal in the first group, which is around 2 times less than in the second group, where around 60% of mosquitoes didn't feed. But I didn't stop the experiment here. I wanted to see how that unique insecticide exposure would influence the way mosquitoes feed for the rest of their life. So each mosquito had the opportunity again to take a blood meal every day of their life directly on my arm on top of the cups. Mosquito exposed once to insecticide took less than 2 blood meal on average over the lifespan, and mosquitoes that were exposed to insecticide while having the possibility to take a blood meal took 1.5 blood meal. Those that were exposed to insecticide without having the possibility to feed at first took around 1 blood meal per female, and in the control group, the method of exposure did not influence the maximum number of blood meal taken individually, which is around 2.5. So the mosquito that took 1 blood meal on the first day of experimentation took around 2 times more blood meal during the life than the unfed female on the first day of experimentation. And we have, so for the unfed on day 1, mosquito took around 1 blood meal per mosquitoes, and when fed on day 1, mosquito took 2.3 blood meal per mosquito. Mosquito exposed to insecticide had on average 8 days shorter lives post-exposure compared to mosquito exposed to a control net. And mosquito longevity was not directly influenced by the fact that mosquito had or not the possibility to take a blood meal while being exposed to insecticide on the first day of experimentation. So until now, we looked at the impact of 1 exposure to insecticide on longevity and feeding success. But I was interested in what happens if mosquitoes are trying to take blood meal in area with 100% coverage. So when a host is protected by an ITN, mosquito can't access the host, except if the net is broken in some places, or the host is laying against the net. So I was interested to know what is the effect of insecticide on mosquitoes that are resistant in these different scenarios. So in a one-way tunnel, I exposed 1,500 mosquitoes, and they had either the possibility to feed against an ITN or an untreated net. So for the specific experiment, a rearing cage with 50 female inside was linked to another similar cage with a plexiglass tube, and the human food was used as blood source. 600 mosquitoes were exposed daily in this tunnel, and 3 bedlet scenarios were compared simultaneously. So in scenario A, mosquito had a direct contact with the ITN lying against a human foot. In scenario B, mosquito had to go through a whole net before being able to take a blood meal. And in scenario C, mosquito faced an intact net and couldn't take any blood meal even if they wanted to. So every day I would look at host searching, blood feeding, and daily survival. What we see is that the presence of insecticide in the tunnel reduced host searching by 45% and blood feeding by 56%. And on average, mosquito exposed to an ITN visited the host around 2 times, which is 2 times less than in the control group. They took 1.4 blood meals per female against 3.5 blood meals per female for the control group. And the net protection also influenced these numbers. Having access to a host through a damaged net reduced the blood feeding rate from around 3 blood meals for the intact net to around 2 blood meals for the damaged net. So the mean mosquito longevity was 21 days, and mosquito having no access to the blood source, so with the intact net, had a 3 days shorter lifespan than the average. Mosquito tested daily in the tunnel with the ITN had a 6 days shorter lifespan. Two less days for those having a direct access to the food through an ITN, and 9 and 7 days less for mosquito exposed to an intact net and damaged net. Also in the control group, having the opportunity to take a blood meal increased the lifespan, and both mosquito having a direct access and those having to go through holes lived 28 days. Those having no opportunity to feed lived around 24 days. So based on the data collected during my PhD, Melissa Iacovidou, a PhD student in Dr. BARREAUX's lab in Warwick, created this age-dependent model to assess the impact of resistance on malaria transmission based on blood feeding rates, longevity, and parasite development time, or EIP. So the vectorial capacity assumes that a mosquito takes an infectious blood meal, and in order for it to become infectious, it must survive the EIP. So after surviving the EIP, the mosquito will take infectious blood meal up until its death. Now, the transmission model is affected by 2 factors: the survival until parasites are matures and the number of blood meal past this maturation. On this slide, we see first how the probability to survive EIP after an infectious meal is calculated. So on the left, there is a much higher mortality rate in the treated group. And on the right, we see in purple the age-independent probability to survive EIP after an infectious meal, which is a constant, which is the mostly used in the malaria transmission model. And in green and yellow, we have the logistic and Gomper's fit, which are age-dependent. It shows the probability that the mosquito survives the EIP given that it takes an infectious blood meal at age A0. And of course, the shaded area represents the error propagated from the parameter estimates. And here we calculated the expected number of bites a mosquito will take by taking into consideration the survival, the EIP, and the age when the mosquito takes an infectious bite. So on the right, we have heat maps on the probability that the number of bites is equal to some K given that the mosquito exceeds the EIP at age A1. So the error bars on the mean markers represent the propagated uncertainty due to the margin errors of the fitted parameters again. And note that since we are assuming an exponentially distributed EIP, it is technically possible the mosquito exceed the EIP at a relatively young age, for example, age 5. Finally, on the left, the violin figure shows vectorial capacity reduction relative to untreated nets for different mortality function, and the percentage of the treated case relative to the control for age-independent mortality is at 43.5%, which shows that multiple exposure to the nets had a significant effect on the vectorial capacity. And in addition, there is a difference in the vectorial capacity between the two age-dependent function and the age-independent function. So for the logistic function, the percentage is at 25.6%, and for the Gomper's, 25.6%, highlighting the impact of incorporating age in the mortality rates. So these results clearly show the importance to develop new methods to characterize the vectorial capacity of mosquito exposed to insecticide. So as a postdoc at the Liverpool School of Tropical Medicine, I now work with Hilary Ronson, Philip Mackle, and Geraldine Foster on a Bill and Melinda Gates project, the Essential Project. So the goal is to develop entomological indicators to assess the effectiveness of new generation bed nets, and together with 6 partners, so 4 African institutes, Imperial College, and the University of Warwick, new methods are tested and implemented in malarious regions, and the results are compared with the gold standard in Maya vector control. So I mean by that experimental hot trials. Today, I will focus on the baited box methods, but I will first briefly introduce the VICTA and room tracking methods. So here we see a modified version of the classic WHO contest, where mosquito movement is filmed during a 3-minute exposure to the bed net, and the movements are tracked with the software to measure net contact. And this method is called VICTA. Here, another method we use in the project. A human host is sleeping under a bed net, and the camera is tracking mosquito movement inside the room. So on the right, we can see an example of mosquito movement over time for insecticide-sensible mosquitoes and resistant mosquito exposed to an interceptor IG2, which is a bed net with alpha-cypermethrin and pyrethroid chlorphenapyr. So the track in blue represents early movement, and the track in red, the mosquito movement 1.5 hours to 2 hours post-release. Almost no movement is detected with sensible mosquito after 1 hour. But today I will focus on the baited box, which allows the study with precision the interaction between a single mosquito and the bed net. So it was designed to observe and measure multiple parameters involved in host searching behavior when the mosquito arrives and lands on the net in response to a host stimuli, and also feeding behavior. So the test is performed in the dark to mimic the time when mosquitoes are most active during the night. And for that reason, an LED lamp and a diffuser are used in addition to a camera. So the host can choose to use its finger or arm to attract mosquitoes. The system can be set to allow a mosquito to feed on the human host through a bed net, or blood feeding can be denied. So the first method simulates a mosquito searching for a host laying against a bed net, and the second method simulates a mosquito searching a host which is not accessible through an intact net. And today I'm going to present key results using the feeding permitted version of the baited box, using my arm to feed a mosquito. So here is how it works. First, we can measure the time to appearance in the box. So at the beginning, the mosquito is in the acclimation chamber, and it's only when it's interested in the human arm that it will come out and enter the box. Then we can measure the time until the mosquito contacts the net for the first time. So in this video, the first contact was also the first landing, and the mosquito found the host relatively rapidly. And then we can look at how long it takes for mosquito to probe for the first time, and finally insert the proboscis into the skin. So from the moment the mosquito finds a blood vessel, the blood begins to be apparent in the abdomen, and the mosquito is feeding. So when the abdomen begins to be full of blood, most of the time the mosquito starts to defecate while finishing the blood meal, and you can see droplets of blood that are expelled at the tip of the abdomen during feeding. And at this point, the osmosis and ionic regulation start, and the metabolic waste is rejected. So when the blood meal is finished, the proboscis stops pumping, you will see that soon, and the mosquito will then find a place to rest to continue diuresis. Here we go. For this experiment performed in Liverpool, I tested 305 mosquitoes individually for 10 minutes. Mosquitoes were resistant to insecticide, and I exposed them to an olisset, a permanent 2, or an untreated net. There are several parameters that can be measured using the baited box, and today I will focus on host searching efficiency, blood feeding rates, and blood volume. So the interest in the blood source, the feeding success, blood meal volume, blood feeding and defecation time, time spent flying, the number of landings coming back and forth on the net, and willingness to stay on the net after feeding. And these are the results I found. So olisset is shown in light gray, the permanent 2 in gray, and the untreated net in dark gray. The figure 1 shows the time spent flying inside the box. The figure 2, the number of landings, or the number of time mosquito are landing on the net, and then they go away and then they come again. And then the figure 3 shows the proportion of mosquito flying away from the net. So the willingness to stay on the net after feeding is measured to see whether or not mosquito try to avoid long exposure to insecticide as much as possible once the blood meal is done. Overall, the figures show that the presence of insecticide increased the excitability of mosquitoes, and they spend more time flying inside the box, avoiding the net compared to the control group. Interestingly, also, they spend much more time jumping on and off the net in the presence of a permanent 2, suggesting it is irritant to them. Similarly, the presence of insecticide results in a much higher proportion of mosquito flying away from nets after the blood meal. Here, the color code is the same, and the figure 1 shows the proportion of mosquito entering the box, or the proportion of mosquito interested in taking a blood meal. The figure 2 shows the blood feeding success, or how many mosquitoes ended up taking a blood meal, and the figure 3, the blood meal volume actually taken by fed mosquitoes. And I found no difference in the proportion of mosquito entering the box, and there is no difference for blood feeding success and blood volume between the olisset and permanent 2 treatment. But in the presence of insecticide, the feeding efficiency is reduced. And thanks to the baited box, we can conclude that ITNs have anti-feedant properties against insecticide-resistant mosquitoes, and the potential for mosquito to be disease vectors is reduced thanks to ITNs. Finally, in this figure, we have figure 1, the blood feeding duration, figure 2, the defecation time, or the time spent sorting out blood and rejecting the metabolic waste while engorging on more blood, and the figure 3, the proportion of mosquito defecating while feeding. All figures shows the same trend, and in the presence of insecticide, the host searching and feeding efficiency is reduced. So the feeding and defecation duration doubles for the control group, and while almost 90% of mosquito defecate while feeding in the control group, only 67% do with the permanent 2 and only 52% with the olisset. This means that in the presence of insecticide, mosquitoes have a reduced ability to blood feed at repletion, which reduced blood quality probably. The blood volume ingested won't necessarily affect the disease transmission potential, but it could potentially affect the parasite dosage ingested in the host, the capacity to survive the exposure to insecticide, and the production of eggs. So in conclusion, the presence of insecticide decreases not only host seeking, but blood feeding success of mosquitoes. ITNs also kills a large proportion of mosquito before 12 days post-exposure, and overall this result suggests that ITN retain at least some functionality against highly resistant mosquitoes. The presence of insecticide reduces the capacity to engorge blood, and spending a short time in contact with the bed net is maybe, treated net is maybe a strategy to lower the insecticide dosage received by blood feeders. And this could be a behavioral adaptation of mosquito living in an area with high use of ITNs. So whether similar results are observable in malaria-infected mosquitoes is unclear and needs further investigation. So until now, I worked with mosquito strain with multiple resistance mutation, and I cannot differentiate the effect of a single mutation on the efficacy of vector control tools. And I think there is need to better understand how specific insecticide resistance mutation affect live history traits in mosquitoes. So Dr. Linda Grigoraki, a postdoc at LSTM, created two transgenic strains with single mutation, so L1014F and V402L. And these two mutations are often found in linkage in nature. And briefly for the method, she injected eggs from a susceptible strain customer with an appropriate CRISPR-Cas9 donor mix, which resulted in a CRISP-induced homology direct repair and the conversion of the wild-type allele to a mutant allele. So only the individuals that were expressing the red fluorescent protein expressed from the CRISP plasmid were kept and back crossed with Kestrel individuals. So the Kestrel female and new female mated with new males. And a subset of the pupil cases were screened for the presence of the mutant allele. With these new strains, Linda found that the introduction of the 1014F allele was sufficient to reduce mortality of mosquitoes after exposure to a deltamethrin-treated bed nets, even as the only resistant mechanism is present. She also shows that mosquito carrying the 1014F allele in homozygosy show fitness disadvantage. As we can see on the figures, it includes increased mortality at the larval stage, a reduction in fecundity and adult longevity. And this can have huge consequences for the strains of selection that will apply to this allele in the field. So I recently got a small grant to study the L1014F strain further, together with the V402L strain, and I hired a recent assistant to help me with mosquito rearing and the experiments. So, in fact, the knowledge gap on the evolution of resistance impact the design of mitigation strategies, and as we saw earlier, resistance mutation carry fitness costs, potentially reducing mosquito ability to reproduce and survive. The costs can be even stronger in a stressful environment where nutrition is limited, increasing the resource allocation trade-off between survival and reproduction, and impacting the mosquito foraging strategies, which determines blood feeding rates and malaria transmission potential. So while homozygosy for L1014F has fitness disadvantage, so reduced survival and fecundity, as we saw earlier, V402L is more recent and expected to have lower fitness costs. So I aim to understand how fitness costs may drive resistance evolution and impact malaria control. I am now comparing the fitness costs of these two genetically related transgenic mosquito strains with unique mutation under larval food deprivation. So I followed the method used during my PhD with field-derived mosquitoes, where I found that figure 1, the larvae pupate more than the average when reared with the high larval diet, and more mosquito pupate in the low larval density environment. In the figure 2, with the high larval density cut in 3, the emergence rate is more important, and a similar trend was found for a high larval diet instead of a diet cut in half. In the figure 3, we see that being fed with the standard larval diets accelerates the pupation time by almost half a day compared with the restricted diet. Figure 4 shows that mosquito reared with less larval food were smaller, took less blood meals during their life as adults, but survived longer compared to those reared with the high diet. So these results were obtained from tunnel experiment, and I would like to use the baited box for a better and individual assessment of mosquito behavior with these two strains. So for this experiment, L1014F and V402L and susceptible mosquitoes will be reared individually with standard larval food or half diet. And the female are given opportunities to blood feed and lay eggs every 4 days until death. So to compare the fitness cost, I'm measuring larval development time, pupation, blood feeding, and egg laying rates, longevity, and also offspring development and rearing. It will confirm whether these strains with decreased fitness costs are potentially better malaria vector. And I think that to better understand the impact of insecticide resistance on the efficacy of vector control, there is a need to study the trade-offs between the energetic expenses that leads to different foraging strategies in recent mosquitoes exposed to stress. Specifically, how many blood meal potential disease vectors can take during their lifespan. So while resistant mutation generally reduce fitness, one can maximize reproductive success by investing more or less energy in blood feeding, fecundity, and longevity. So the optimal foraging strategy may vary depending on the resistance level and the environment. So my hypothesis is that nutritional stress aggravates the fitness cost of resistance and impacts foraging strategies, especially for the mosquito carrying the older KDR haplotype, so L1014F. The second aim of my project is to test whether the newer V402L KDR haplotypes might outcompete the L1014F haplotype, which has high fitness cost. And my hypothesis is that in comparison to L1014F, we expect V402L to have lower fitness cost and more chance to persist in the absence of insecticide in a mixed population. So to answer that question, I will crossbreed the two mittens, and the offspring will be reared as a new strain over multiple generations. And the subset of each generation under larval nutrition pressure or not is screened to measure the allele frequency for both mutation. It will confirm whether high resistant costs decrease L1014F allele frequency compared to V402L. So in the future, I will also like to explore the impact of resistance mutation on lifelong feeding success in the presence of insecticide as well as malaria parasites. I'm also interested in the carryover effect of larval food deprivation over multiple generation of mosquitoes. And if my work interests you, please do not hesitate to contact me. I'm very much open to new collaboration and happy to discuss with you about the development of new research ideas. And finally, I want to acknowledge my collaborators, Matt and Jacob, my PhD advisor, Raphael and his larval collection team in Côte d'Ivoire, my current PIs, Philippe, Geraldine, and Hilary, and all the associated lab members, as well as the people taking care of the VK7 strain in the insectariat at LSTM. I would like to thank Lauren, my research assistant, and my collaborators Linda for the creation of transgenic strain, and Melissa and her PIs for the mathematical modeling. Thanks for listening.
Merci beaucoup, Priscille, c'était très intéressant. Et ben, on va pouvoir passer aux questions. Donc, elles peuvent être posées soit en français, soit en anglais, soit directement en ouvrant vos micros, en levant la main ou par le chat, comme vous le souhaitez. Bon, si personne ouvre le bal, je vais le faire. Moi, j'avais juste une petite question de technique pure sur l'expérience où vous suivez les déplacements du moustique autour de la cage où la personne est allongée. Comment vous arrivez à suivre les déplacements du moustique?
En fait, il y a deux caméras de chaque côté qui enregistrent les mouvements des moustiques. Donc, il y a à peu près 50 moustiques dans la pièce. Ouais. Et tu as un logiciel après qui va suivre chaque mouvement des moustiques. Donc, c'est un logiciel, quoi.
Ah, d'accord. Ouais, super.
Si vous êtes intéressé, je peux vous mettre en contact avec mon collègue qui a développé le logiciel.
Ah, bah, avec grand plaisir. Parce que c'est vrai que sinon, les suivre un par un, ça peut être un peu long, quoi.
Oui, c'est la méthode avec la baited box, mais c'est plus petit, c'est plus long. Et puis, bon, le baited box a l'avantage d'être plus précis parce que c'est un moustique un par un où on regarde le comportement. Pour le tracking room, c'est plusieurs moustiques et les mouvements sont mis ensemble. En fait, on ne sait pas exactement quel moustique fait quoi à quel moment.
Oui, c'est plus pour avoir un pattern général.
Oui. Exactement.
Super, merci beaucoup. Ah, je vois qu'on a une question dans le chat de Margot qui demande quelle est la différence entre Olicet et Permanent 2.
Permanent 2, c'est du delta. Donc, les deux sont avec du pyrethroid. Permanent 2, c'est avec deltamétrine et Olicet, c'est avec permétrine.
D'accord. Elle vous remercie. Ah, Michelle?
Hi, great talk. I just had a question. I might have missed it at the beginning, but when you were following some of the blood meals following exposure to the insecticide treated nets, did you see any like behavioral changes like to sip feeding where a mosquito might feed not to completion and then go back either several hours or several days later to bite again?
So I don't know which experiment you're referring to. So I've done experiment in the cup assays where mosquitoes were exposed to insecticide, and then every 6 hours I would give them the opportunity to take a blood meal, and then every day after that. And we can see that mosquitoes that were pre-exposed to insecticide were less efficient to take blood meals compared to the mosquito that had direct contact with my arm through the bed net. So there is that. And I also tested the mosquito inside tunnel every day. And that was a 30 minutes experiment every day. So I don't know if the ones that went on the other side would come back again during this 30 minutes. I don't know, because I was only looking at how many mosquitoes were on the other side every 10 minutes and how many mosquitoes were fed. So I don't know what they did during that time. And also I don't know if mosquito that didn't want to take a blood meal at that moment would take one hour later or something. I don't know.
Oh, cool, thank you.
J'avais une petite question, si c'est possible. Allô?
Oui.
Ah, ok, parfait. Merci pour cette présentation. Hein. Après, j'avoue, je suis resté un peu sur ma faim. Je m'attendais un peu plus de détails sur cette partie modèle structuré en âge, qui est notamment mentionnée sur le résumé. Il y a une équation qui est passée un peu rapidement lors des diapos. Je n'ai pas vraiment eu le temps de voir exactement qu'est-ce qui est derrière le modèle mathématique dont vous parlez. Ça m'a un peu échappé, je pense.
OK. Donc, je n'ai pas détaillé le modèle. Ce n'est pas moi qui l'ai créé, ce modèle. C'est en collaboration avec mes collègues de Warwick. Et je voulais juste montrer qu'en mesurant, en créant un modèle où on a un age-dependent mortality, donc où la mortalité n'est pas constante, on a vectorial capacity qui est totalement différente.
Ouais. Ouais, ça j'ai bien compris, mais après j'ai essayé de fouiner un tout petit peu le préprint, on en parle un peu. Et après, peut-être, vous me dites peut-être c'est votre collègue qui est mieux de répondre à la question, mais je la pose quand même. Est-ce qu'il y a également la prise en compte de l'histoire de l'infection je sais pas, du moustique, quoi? C'est-à-dire, est-ce que vous regardez en même temps non seulement l'âge, et ça j'ai bien compris,
Non,
mais également...
malheureusement, non. Ça serait
Ah,
vraiment intéressant.
d'accord.
Donc là, c'est un paramètre qu'on a amélioré pour
Ok,
la longévité. On
d'accord.
est en ce moment en train de travailler sur age-dependent feeding rates. Donc, dépendant de l'âge, le feeding rate va changer. Donc, c'est pas un feeding rate constant.
Ok.
Mais je suis tout à fait d'accord. Ce serait vraiment intéressant d'avoir un meilleur EIP pour ce modèle-là encore.
Ah ouais, je comprends. Ok. Ben, merci.
Ça n'a pas été fait encore.
Ah, je comprends.
Bonjour, Fred. Je ne mets pas ma caméra, je suis sur mon téléphone. Bravo, bravo pour ce magnifique talk. J'avais juste une petite question. Est-ce que tu contrôles le taux oh, ça m'échappe, de fécondité de tes femelles, si elles ont été fécondées ou pas?
Alors, j'ai suivi ça dans les expériences avec le tunnel, mais je ne les ai pas présentées aujourd'hui. Et selon les réplicas, j'ai des résultats un petit peu étonnants. Donc, des fois, mes femelles, elles ont pondu.
Le taux d'insémination, je voulais dire.
Ok,
Est-ce que
non,
tu
non,
vérifies
j'ai
que
regardé.
tes femelles, elles ont été accouplées avant tes expériences? Est-ce que tu as moyen de le faire?
Alors, la seule chose que j'ai fait, c'est une expérience pilote où j'ai regardé si les femelles étaient
Inséminées?
inséminées.
Il y a un problème avec ce terme.
Oui, pardon, mated. À 3-5 jours à peu près. Donc, généralement, c'était plutôt, j'essayais d'être précise à 4 jours, mais bon. Mais à part ça, je n'ai pas à chaque expérience regardé si elles étaient inséminées ou pas. Non.
Tu pourrais le contrôler a posteriori, par exemple, soit en disséquant
Oui,
les spermatèques, soit en recherchant par biomol un marqueur Y, quoi.
oui, tout
Et
à
ça
fait.
serait peut-être
Mais
un bon
oui,
contrôle à envisager, je pense.
oui, je
Et
suis d'accord.
merci encore pour cette présentation.
Avec plaisir.
Okay, hello. So thank you very much for the talk. It's very interesting, and it's always nice to see the details that we can pull out in the laboratory. But ultimately, I guess we want to be able to compare what we've seen in the lab with what is actually happening out there in nature.
Yeah.
So do you know anything about what the frequency of multiple blood feeding or the number of oviposition events for resistant mosquitoes compared to sensitive mosquitoes in natural conditions?
No, I don't know. I'm sorry.
It's not a question of being sorry. It's a question that the ability to evaluate what we see in the laboratory against what happens in nature. But
Okay.
if you don't know there, it's possible some of the people listening might have an idea and they could chip in with that. But I think it would be something it would be nice to complement instead of having a 100% laboratory based or even a semi-natural, if at least we have an idea of what is the longevity of resistant mosquitoes or how many ovipositions they make or such data that's you're measuring in the laboratory. If we can have an idea in the field, I think that would be nice, a nice complement.
I'm very much happy to discuss further with the expert in this. Thank you.
That was the point I wanted to make. Thank you.
Alors, il y a deux questions dans le chat. Donc, tout d'abord, une deuxième de Margot qui demande si ces études ont eu lieu chez d'autres vecteurs de la malaria.
Pas que je sache.
D'accord, super. Et la seconde question donc, vient d'Herman qui demande sur quelle base a été définie la concentration des insecticides pour l'expérience et aussi savoir le niveau de résistance dans la zone d'étude.
Alors, pour tous les insecticides utilisés, donc je disais insecticides, mais c'est à chaque fois des moustiquaires qui sont distribués dans les pays endémiques. Donc, c'est toujours des concentrations définies. C'est pour permanente 2, c'est toujours la même chose, permanente 3 ou LI7. Donc, voilà, j'ai pas cherché à faire des doses différentes. Je voulais que ce soit le plus naturel, entre guillemets, possible ou le plus proche de ce qu'on peut trouver dans la nature.
Oui. Super, merci. Caro.
Yes, thank you very much for this very nice talk. My request is more for a comment rather than a question. And well, everyone knows that vector control with insecticide treated nets has been extremely important, useful, and efficient to reduce malaria incidents across Africa in the last 20 years or so. But there has been in the last years malaria control stalling. So the incident rates has kind of reached some kind of plateau.
Yeah.
And so I'd like to see these results within this picture, within this framework. How can we explain, given that there's so much resistance and people have been talking about resistance as one of the main factors leading to these, how can I say, not failure, but at least stalling in malaria control. So how can we interpret these results within this picture? I mean, if I gather the main message of your results is that even with highly resistant populations, you still have quite significant effects on vectorial capacity. So, so why everyone is talking about resistance as a problem for malaria control?
It's an excellent question. So resistant, so it's a comment, so I answer. Okay, insecticide resistance is a threat, and lots of study went out showing that exactly, but the link exactly on the rise of insecticide resistance and the malaria transmission is the link between the two is not really clear. It's not really clear that because we have more resistant mosquitoes, we have more malaria transmission. Now, why is insecticide resistance, why is malaria transmission not going down after all these years? It's a really good question. I think there is many parameters that we need to take into account. So are people using the bed nets? Are the bed nets used correctly? And for how long? And if they are used, do they still keep using it? Are the bed net used in certain region adapted to the resistance profile in the field? Well, there is many questions that needs answers, and I have no idea why we don't find a link between these two, insecticide resistance and malaria transmission yet.
Okay, thank you. And if I just may add one other comment is that we are interested in studying carryover effects and we are developing tools to do that. So we may possibly discuss about this.
Excellent. I'm happy to discuss with you then.
Je pense qu'on a fait le tour des questions. Si quelqu'un en a une dernière. Ça a l'air d'être bon. Et bien, Priscille, merci beaucoup pour avoir pris le temps de partager vos recherches avec nous. C'était vraiment très intéressant. Et merci à tous d'avoir assisté à ce séminaire. Et donc, on se retrouve dans 2 semaines pour le prochain.
Merci Sophie pour avoir organisé ce séminaire.
Merci.
Et merci à tous d'avoir écouté.